In this video, I thought it would be good to sort of break up the monotony and look at some visualizations. What exactly are these Taylor polynomials? And also use this as sort of a bridge to something a bit bigger, right? Because I mean, the polynomials are okay, but they're bigger fish to fry, so to speak. So I have three animations that I want to look at. And let me just kind of summarize what the first one is. So for instance, the function is the sine of x plus 2 cosine of x. And I am going to show an animation where it shows that function, and then we're going to look at the different Taylor polynomials that approximate that function. I just chose x equals 1, right? Now, if we were doing this by hand, x equals 1 would not be a convenient value to choose, but we're not doing it by hand. Maple is doing all the calculations, and it's super powerful, so it can handle this stuff. So let's go ahead and take a look at this. I'm going to hit enter, and it produces this. So I'm going to make this plot just a little bigger so we can see what's going on, right? And there we go. So what do we have here? Notice we have our little key at the bottom. So the original function is that reddish brown. And then we have our first degree Taylor polynomial. And notice it's right at x equals 1, right? So it's not at a nice convenient value of x. So if I just go to in fact, let me go ahead and adjust the frame per second so it's not too fast. Let me bring it down to 3. So what I'm going to do, I'm going to hit the play button. Well, actually, before I hit the play button, let's just look at the next frame. So the next frame is going to now show us what the second degree polynomial is. So I'm going to do that. And there it is. So it's a quadratic, but you can see, in fact, let's back up a little bit. So there's the first degree, there's the linear Taylor polynomial at x equals 1, and then there is the quadratic. And you can see there is a better fit to what's going on. Let's see what happens if we use a third degree Taylor polynomial. Okay, so it's not great, but look at, it's certainly a pretty good fit here. Definitely not a good fit here, and then it just kind of, crosses our function. And if we think about third degree polynomials, yeah, they tend to go off to plus or positive and plus or minus infinity in both directions. So we can see it going down here and going up here. So let's continue to increase the degree of this. So let's go to the next frame. So there's 4, there's 5, there's 6, there's 7. So I did a lot of these. So I'm just going to hit play now, and we're just going to watch to see what happens as we continue to increase the degree of our Taylor polynomial. So there it is. And it goes a little fast. But notice what happens. As the degree increases, the polynomial, which is in blue, right, is starting to, essentially fit this sine function pretty well. In fact, so well that at the end, so what I did, how high was my degree? Up to the 80th degree. And when I look at this, I can't tell the difference between the two functions. Everything is like perfectly overlaid, right? You want to see that again? Let's start over. In fact, we can sort of do this in reverse, but I'm just going to slide it back here. There we go. And maybe even go a little slower so you can actually see this. So as we progress, there it is. All these blue polynomials. And I know the graph doesn't look great, but yeah, it's just, these are polynomials of a very high degree. So I could increase the number of points, and then it would kind of smooth it out while the animation is going. But at the end, you saw that it kind of smoothed it out on its own. But there are all the Taylor polynomials, and the higher the degree, the better the fit. The higher the degree, the better the fit. And look at the window that I'm in. I'm going from negative 8 pi to 7 pi. And it turns out with your sine and cosine functions that just, oscillate, no matter how high the window or wide the window I use, I can always find a degree that will fit it in that particular window, right? So then you have to ask yourself, could I, in theory, find a polynomial at one of these, well, it wouldn't be a polynomial now, but what if our polynomial had an infinite degree? Because if you think about our sine and cosine curves, they oscillate indefinitely for, all real numbers. So could I find something like this that basically is a sequence of polynomials where the degree just keeps getting higher and higher and higher, and that sequence essentially converges to the sine function? That would be really interesting, right? Okay, so there is the sine. Let's look at the next one that I have, and this one, it won't be as long. This one, I see the function that I chose, it was e to the negative 3x plus 2x minus 1, and then I chose x equals 2 as my point of tangency. So let's go ahead and see what that one looks like. Yep, I mean, certainly not as visually appealing as our sine functions that oscillate indefinitely, but the red function is our exponential function. And notice this one, the function itself now goes off to infinity. And you can see right here is the point of tangency. And you can see that what we have here is our Taylor polynomial of degree 1. So again, I'm just going to go through frame by frame. So let's see what the second, okay, not much difference there. Third, okay, I can see something happening. Oh, there's a fourth, fifth, sixth degree, seventh, eighth, ninth, 10th, 11th. And I mean, look at that, with degree 12, almost a perfect fit. So I'm going to back up and I'm just going to run this. But let me again reduce. Each time you build one of these, the default is 10 frames per second. I like it a little slower so I can see what's going on. And look at what, as I increase the degree, that polynomial, it's like it just converges and it just covers up the exponential function entirely. And again, you can't tell the difference. So again, starting out with just the linear, you can see that the linear, it does a good job of fitting this part, but it does a horrible job of fitting this part, right? And it makes sense, right? Your line has constant slope, whereas your e to the negative 3x plus 2x minus 1, it has non-constant slope. So using a function that has a constant slope to approximate a function that has a non-constant slope, that will only work well for, let's say a small set of x values. But if you want to, let's say, have this kind of approximation good for a large set of x values, then you kind of have to up the degree of the polynomial, assuming you're using this method. So let's go through and play, and there it is again. All right, there's our Taylor polynomials, and now I can't tell the difference between, and that one I only needed a polynomial of degree 20. And part of the reason why is because I chose a narrower window than in the previous example. All right, so we got one more of these to show you, and before I show you the next one, I want you to take a look at the functions in the first two examples. And I'm gonna talk about each or identify the type of function each of these, and then there's a property that they have, right? All of these functions. You have your sine function, you have your cosine function, you have your exponential function, and you have we just group this and say you have a linear function. All those functions, right? Sine, cosine, e, and any polynomial, they are continuous and differentiable for all values of x. So it seems like, if you think about it, remember what Taylor requires. Taylor requires that we need all these derivatives to exist so we can build this polynomial. Well, if the functions are always differentiable, it seems like, well, yeah, it should have all the derivatives that we would need to construct this polynomial that eventually will be a perfect fit for these functions. My third example does not have that property. If you can look at it, I chose a really simple function, 1 over 1 minus x. This function is not continuous at x equals 1. And it's not differentiable there. So for one, I could not find a Taylor polynomial at x equals 1. So what did I do? I chose x equals 2. And this animation here is going to show us the linear all the way up to the 20th degree. All right, so let's take a look at this one. Okay, so we see something different. We can see that vertical asymptote at x equals 1. And you know what a vertical asymptote does? It basically splits the function into two pieces. In math we call it two branches, right? So you have a branch over here, you have a branch over here, and you can see that here when I chose x equals 2, so I'm on the branch basically that's on the right hand side of this vertical asymptote. And what's going to happen is, so if you think about it, I am now going to try to approximate a function that is not continuous with functions that are always continuous, right? Polynomials are always continuous. This rational function is not always continuous. And here is what's going to happen when this. So again, I'm going to do it frame by frame. So there is the linear, there is the quadratic, there is the cubic, quartic, quintic. And so do you notice what's happening is only, I guess you could say, a relatively small region of the 1 over 1 minus x is being covered by the polynomial. And as I increase the degree, this part of it just keeps going, it kind of almost oscillates, going off to either positive infinity or negative infinity, but the rest of it seems to be covered pretty well. But unlike the first two graphs or illustrations that we looked at, it doesn't cover the entire graph. It's like it can't cover the entire graph. For one, it's almost like this vertical asymptote is preventing something important from happening. Like it can't get on this side at all. And not only that, but it looks like it's stuck right at 3, right? So like the point of tangency is at x equals 2. It can't go to the left of 1 because of that vertical asymptote. So it's almost like it has to be symmetric in the interval that it covers the original function, right? So again, let's do this fast and well, not super fast, but let's now just play the whole thing. So look at it again. It's like it's stuck right there. It said, nope, this polynomial only works, it looks like, again, from a visual, it looks like the interval 1 to 3. And we know it can't include 1, right? Because 1 is the function isn't even defined there. And then it goes up to 3. So something strange is happening here in the sense that, because our original function is not always differentiable, our Taylor polynomial is having a problem. And what I'm going to do just to illustrate this, I'm going to change the point of tangency just to show you that the number 2 in some sense it's not irrelevant, but it's not just the 2 there are other things at play here. So I'm going to change this and make it -1. Make that x equals -1. In other words, I'm going to put it over here on this side. So let's see. And there it is. Okay, so now I have my linear Taylor polynomial at x equals 1. Seems to be a pretty decent fit once we're close to -1. Let's go through and again frame by frame. There is a second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th. And again, it looks like it. So now here, it's the point of tangency is x equals -1. And it could go all the way up to +1, which is essentially 2 units. But then look at what's going on down here, and then it looks like it extends all the way down 2 units in this direction. But once it gets to -3, and maybe what I should do, let me go ahead and modify this, and just so we get a bigger window. There we go. So now I'm just going to play this, and let's see. Again, something strange is happening. Right, it can only cover a certain part of the original function, right? So the point of this is that there are ways that we can get Taylor polynomials to converge to an entire function, but that function apparently has to do something with always being differentiable, right? Not having weird things like vertical asymptotes like what we can see right now. So we're going to explore this in our next video as we then now extend this idea of a Taylor polynomial, and we're going to introduce the concept of a Taylor series, which is infinite. Taylor series / power series, those are the interesting objects that we get to look at in our next video. See you then.